So I want to do a couple of examples in SCT2. Yeah. So let's do an example. Let's do an example which is in some ways simple. And it's kind of an exclusive analog of our DIS example, and it's called the photon-pion form factor. So it's exclusive. It's clearly exclusive. There's a pion. And really, that all that's going to come in here is kind of hard collinear factorization. So it's simple in the way that it actually is not really exploiting the full complications of SCT2. It's really just another example where we have hard modes factoring from collinear modes, but they're clearly SCT2 modes because they're going to be modes for this pion. So we're going to use, again, for this calculation, a bright frame, which you'll see, I guess, when I write down some momenta. So what would you write down for this process in QCD, first of all? So you'd say I have a pi0, it has some momentum p pi. I have some current, which I can take at 0, and I want to make a transition from the pi0 to a single photon. So you could write that as follows. I can always replace the photon by current. And then I can parameterize that matrix element like a form factor. And if we go through things like parity, charge conjugation, stuff like that, time reversal, we find out that there's one real form factor and there's an epsilon symbol in this guy. It has to be linear in the polarization vector. That was already true here. And there's sort of one way of getting the indices to work out, which is with this epsilon. So what you're really after in this process would be sort of some understanding of this form factor. That's the one piece of non-perturbative information. Everything else, Lorentz invariance is enough to tell you about. So we'd like to see if there's a factorization theorem for that form factor if we take the limit where q squared is large. Okay, so we have an electromagnetic current. Think about it as up and down quarks for the pion. So there's some matrix in the 2×2 space, which is the charge, which you can write as 2/3 minus 1/3, like that. Or if you wanted to write it in terms of Pauli matrices, you could write it as identity over 6 plus kind of a tau 3 for isospin Pauli matrix over 2. Okay, so there's some charge matrix that's going to show up. What happens if we expand for q squared much greater than lambda QCD squared? In this formula over here, this form factor knows about lambda QCD and it knows about q squared, and we haven't expanded. So what happens if we do expand? Can we simplify that form factor? And it does. So I'm going to do this in the bright frame again. And that effectively means I'm taking the momentum that corresponds to the off-shell photon as the same form as we did before for our calculation in DIS. Purely in the z coordinate. The momentum of the photon, it's an on-shell thing, so I can just write it as E of the photon, say, times a light-like vector. Then p gamma squared will be 0, as we want it to be. And if I pick this kinematics, then p pi is just p plus p gamma. And so that would be p pi. Okay, so in Feynman diagrams, what am I talking about? I'm talking about making a transition with an off-shell photon through a diagram like this one to a pi0, or plus the cross graph. And with this setup, with this kinematics, this intermediate line here, if we go through the scaling, it's going to be hard. So these guys, with this kinematics, we make the pion collinear. In order to see that, you could impose pi squared equals m pi squared, right? This is never going to be made small, but E is going to have to be tuned to be basically q over 2. So this thing is going to become, if you impose this condition, something like m pi squared over 2q. And then you find out that the pion is collinear. So the pion is collinear. The photon is a photon. This line here is hard. And so we want to integrate out the hard line and match this guy in the effective theory onto some effective theory operators that would look like this. This guy's pink. OK, so we just have to write down what type of effective theory operators that could be. And again, it's an effective theory operator with 2 quark fields. So it's very much like what we did before. So I'm not going to be going through all the indices that I have to go through in order to keep track of charge conjugation and all those things. I'll just write down the right answers for that part. So I could write it like this. So after doing hard collinear factorization, there's, again, operators, which is 2 quarks, some hard Wilson coefficient, which is this pink thing, integrating out the pink line that sits in the middle. This obeys current conservation. Dimensional analysis fixes this 1 over q. Charge conjugation actually also provides constraints on the Wilson coefficient, so just like it did in DIS. So charge conjugation tells us that there's a relation between flipping signs. If we go through, so we just impose on this operator all the symmetries and things that we can think of and see what it says about the operator. You can think about just writing the operator down based on this picture without ever calculating any diagrams, just knowing what you're after, and then imposing on it all the symmetries that should be conserved. So one is dimensional analysis. That gave the Q. Current conservation, that's partly responsible for the epsilon. Should also look at parity. Go through flavor and spin, and you find that this has this structure, and there's some constant that I threw in here. And you actually know from the flavor that it's got 2 photons, right? And I'm not ever adding any more photons, so that means there's 2 factors of q hat. And so there's a q hat squared, which I can stick inside this gamma. And it has to be a color singlet. because it's going to have a non-trivial matrix element with a pi0, which is a color singlet. And since it has to be, so there's no TA inside the gamma. That's what I mean. There would be nothing for the index A to contract with. And since it's a color singlet, that means if you were to think about soft interactions here, they would just cancel, right? If I were to think about putting in soft interactions and integrating them out, I'd get an S stagger S that would cancel out. So that's the sense in which this is a simple example. OK, so then we would have a formula where we could equate the effective theory result with the full theory result. So we can equate matrix elements. And this is one way in which this example is different than deep inelastic scattering. We're really doing a matching at the amplitude level. So we're getting, remember the form factor was a parameterization of the amplitude. And if we do that, if you think about the two currents that we had, and we've integrated them out, now thinking about just this operator here, the matrix element pi0 to vacuum that we had defining this thing, which had two currents, just becomes the matrix element of that operator. Again, like our DIS example, we form the sum and difference of the momenta, forming p bar plus, which is p dagger plus or minus p. And one of these guys just gives the total momentum, just the minus with our sign conventions. So that gets fixed, which in this case, it just gets fixed to the pion momentum, which is q. So if you like, you've inserted the operator here. You have some linear lines. And then you have a matrix element with the pi0. And then you have gluons. But you know that whatever momentum comes in has to be the momentum of the pion. And that's the one momentum constraint. So that means that the answer just involves one convolution again, which is the one that's unconstrained. So there's a Wilson coefficient that depends on the other unconstrained guy, which is p plus. And then there's a matrix element where I can write in a delta function with that p plus, the usual kind of way that we've done. But here it's a little different kind of matrix element than the one we saw in DIS because it's not forward, it's vacuum to pi0. But it's actually the same operator that we were talking about in DIS. In fact, I mean, it's just a bilinear operator with two linear quark fields. Linear quarks addressed with Wilson lines. So one can go through a similar type of matrix element analysis for this operator, and it gives something that's called the light cone wave function. So let me define that for you. So this matrix element can be written in terms of an object that has a dimensionless variable and it's kind of an analog of the part-time distribution function, but for this matrix element that we're dealing with here, which is vacuum to pion. So this has some similarity to the formula we had in DIS. There's a delta function there. There's a delta function here. There's a dimensionless variable z there. And this is a non-perturbative function. So this is what's called a light cone distribution function for the pion. So generically, when you have an exclusive process and you're producing some hadron that's very energetic, like a pion, this is the type of thing that's going to show up, one of these light cone distribution functions. So this example of photon to pion is in some sense a very, very simple exclusive process, or the simplest one in some sense. OK, so we could take this formula, plug it back in there, and then we'd have a factorization theorem. And I think that you can imagine what that would look like. I could write it instead of an integral over w as an integral over z. And that would be the factorization theorem involving this phi pi. So
is this at the same interpretation, the probability of the pion?
Yeah, that's right. So you should think of the z as like, so the way to think about the z is as follows. So think about like when you initially produced these guys here. Think about all the momentum going this way. When you initially produced them from this after you integrated out the hard interactions, you had z and 1 minus z is the possible split of the quarks fields in the operator. So one of these guys carries z. Effectively, what this 2z minus 1 is doing is one of these guys is carrying z, and one of them is carrying 1 minus z. OK? The sum of these is 1, and that's the analog of the statement that the whole total momentum should be the pi0 momentum. But you don't know how to split how much goes into each one of those. And what the wave function is, it's kind of all the linear interactions that subsequently rearrange this thing before you sort of annihilate it with the state. So, I mean, all these things are like dressing up the pion state. You know, they're producing the pion pole, so this is like phi pi. And so what you have is an operator that depends on z, a wave function that depends on z. So this is a Wilson coefficient that depends on z. And your final factorization theorem is exactly of that type, that you sort of have an integral of c of z, which also can depend on q and mu, and then phi pi of z and mu.
Is it sensitive to phi pi z is universal?
Yeah, it's universal.
You can use it for other exclusive processes?
Absolutely. Yeah. So as long as you can factor it so that it's these fields and that pion, then you have this matrix element, and you get this guy. So people try to measure things about this guy, its moments, and stuff. All right. One thing that happens here has to do with this integral over z, which is kind of this is kind of in some sense an unsolved problem in SET. So I have to mention it. So when you do this integral, you could ask, what does this c of z look like? And it turns out that c of z will have in it terms that go like 1 over z. And so you get integrals that look like dz over z of phi pi of z. So say at lowest order, this integral would show up. And it turns out that for this matrix element here, you don't get anything worse than that. You never get 1 over z squared. And this integral here, because of properties of this phi pi, is finite. There's no problems. But there are examples known in the literature where that's not the case, where you actually get 1 over z squared. And people have some understanding of the physics that's happening in those cases, but there's not a complete understanding of how factorization works in those cases. Okay, so that doesn't happen in this example, but there are other examples of exclusive processes that would lead to 1 over z squared, and then this integral is not well defined. And people kind of understand that there's a cutoff that's coming in, and that they understand that that cutoff actually has to do with some rapidity, but how to explicitly write down an analog factorization theorem that involves those cutoffs and has a renormalization group is an unsolved problem. Unsolved SCET2 problem. Okay, but for the example we did, everything's kosher and beautiful.